Welcome back, everyone, to MATA35. This is, I'm counting this as lecture 4, since I'm counting each 50-minute chunk as a lecture, even though we have, so basically on Wednesdays we have two 50-minute lectures, and so this is why this is number 4, even though it's actually only the third day of class. And one of the things I thought we'd do today is I feel a little bit bad about going so fast on u-substitution and integration by parts in the last lecture. It felt like a lot of people really didn't click for them. And so I thought I'd go over it a little bit more slowly and also try to give you a couple more hints as to how to correctly guess the substitution or the separation of the parts. These are all heuristics. Unfortunately, the only way you're going to get good at these things is by lots and lots of practice. And so if you look on the course website, I have mentioned a couple places. Oh, sorry, let's show lectures. So I've mentioned a couple places in your textbook where there are just a lot of practice problems. So, oh, actually, why is this not? Ah, there it is. Yep. So practice problems for u-substitution, for integration by parts, and the other topic we'll be learning today, which is numerical integration. So you really do need to practice these problems. I know I'm not requiring you to turn in homework, but you need to get really fast at least is the thing, because these are basic building blocks that you'll have to use for the later analyses. And so even though doing each one individually, if you do, it takes some time, you might be able to do it slowly, you really need to be really, these should be as natural as addition and subtraction. Okay, having said that, let's go ahead and get started with today's material. So let's go back to the substitution rule. So I gave you an algorithm last time, and there were a couple weird things about that algorithm, right? So the very first step of the algorithm was I told you to guess. Now, that unfortunately is not a very useful rule, right? Because, like, what do you guess? And so that's the question that we're going to try. And so the answer is, well, you don't necessarily know what change of variables is best, but there are a couple heuristics you can use to try to figure out a useful change of variables. They don't always work, and you won't always know whether or not there is a good change of variables, but it is still useful to have a few heuristics. So what is a useful change of variables? And by change of variables, I just mean changing from an x variable to some u variable that's a function of the x's. Okay, so to do this, let's go back and look at a couple easy u substitutions. So let's start with an example. And I don't think I did this one yet. But so let's suppose I have the integral of a fraction 3x squared dx. I'm going to write the dx on top for reasons that'll become clear in a moment. And then let's say on the bottom is 1 plus x cubed. So now, if we have that, what are the different possible u substitutions? So let's start first with the correct guess and see what happens. So if you guess u is equal to 1 plus x cubed, so the stuff in the denominator, then what you're going to end up getting is du is going to be equal to 3x squared dx. So then that turns this entire thing. You can substitute that in since you have this 3x squared dx, and that's just the stuff up here. So this entire thing is just the integral of du over u, or 1 over u du, which is just the natural log of u. But now, what happens when you pick the wrong u substitution? Say you guess that u is equal to 3x squared. Well, then what happens? Then when you take du is equal to 6x dx. But is there really any good way, like 6x dx doesn't really appear in your original integral. And so you could try to force the substitution in, but it's not going to make things simpler. It's going to make things more complicated. Let's see another example of that, where this will become a little bit, hopefully a bit more obvious. So let's give another example. And suppose I have an integral of sine squared x cosine x dx. So we have a couple different choices. So let's start with if you so we try to make the du cancel something out. It's not quite cancel something out. You're trying to make it so that you see the du basically in your original integrand. So you choose some u that appears there, and you also choose some du that maybe it doesn't exactly appear there, but it almost appears there. And when you do that, what happens is your new form is simpler, because you can make u anything you want, and then you can solve for x. But often that's going to make your integral a lot more complicated. So we'll see that very shortly. So Let's again try the correct integral. It's correct substitution, or a correct substitution. There are often different choices that'll work. So u is equal to sine x. So then du is going to be equal to cosine x dx. And again, this is nice because we have our cosine x dx, which appears right there. And our u is sine x, so this turns into the integral of u squared du, which we all should know how to solve at this point. But now let's suppose we tried the other one. So suppose we tried u is equal to cosine x instead. Yeah, so the square is because of remember that this notation here for sine squared means that it's sine of x squared. And so that's why we have this u squared there. So it's not necessarily that it'll be the two different parts of it. It's just that the u will be one piece and the du will be another piece. And then when you put them together, but it's not in the... Oh, yeah. So just a reminder about notation. This is one of the bad things about mathematicians. Sometimes we have confusing notation. So just as a reminder, let me put this in green up here. If I say sine squared x, that's equal to sine of x squared. It's just one of the weirdnesses with mathematician notation. But yeah, so hopefully that answers your question about where the the squared went. So the squared was always outside of the sine x. It's just that mathematicians write things weird sometimes. Yeah, okay, so going back, so what's du here if u is equal to cosine x? Well, du is going to be equal to minus sine x dx. So you might be thinking, this all still sort of works, right? And the other thing is you can also just explicitly solve for x. So then x here would be equal to cosine inverse of u. Okay? So then when you convert this all together, what you end up getting is minus the integral of sine x cosine x du. Because du is minus sine x dx, and so when you multiply that in, you get the right thing. But of course, you want to get rid of all the x's. And so this is equal to minus the integral of sine of, well, the cosine of x here turns into just another u. But the problem is the sine of x doesn't, so you end up getting sine of cosine inverse u, all of this times u du. Now you'll note that this is super hard to integrate. We don't have an easy rule to do that. And so because of that, when you want to change your variables, what you want is, after substituting in the u and du, the equation is simpler. And it's often a good sign if the u and the du both appear in the original integral up to a constant. And the u can be some function. Like here, it's part of the squared function. So you have sine of x and you still squared, and that's still fine. But the du should appear more or less in the original integral up to a scaling by a constant, since you can always multiply or divide by a number, and that still keeps integrals similar. So let's try that out. So this is the basic idea. What is the u-substitution? Let's do this for this first one here. So what would you guess is the u-substitution? Is it x to the fourth, this piece on the left? Is it x to the fifth, the stuff in the e to the in the exponent? Is it e to the x to the fifth? Is it x to the fourth? Okay, yeah. So it looks like people are replying a ton of B's in the chat. So this is correct, and let's actually see this very quickly, and that was the right thing to say. I thought the u and du together should be... No. So there's a comment from Samantha. The u and du... so for u substitution, the u and du don't have to be parts of the whole original function. That is true for integration by parts, which we'll cover on the next slide. But for u substitution, the du should be part of the original function, but the u can be just some other thing that appears as part of the function, which is one of the subtle things that you have to be careful about. So what happens here is u is equal to x to the fifth, and du is going to be equal to 5x to the fourth dx. And so this entire equation turns into the integral of 1/5 e to the u du, which you can solve because the integral of e to the u is just e to the u, so this is 1/5 e to the u plus some constant, which is going to be equal to 1/5 e to the x to the 5 plus some constant. Excuse me. Okay, let's try that again. So hopefully you guys see what we're doing. Let me reset this quickly. So For the next one, we have e to the 4x dx. So which of these is the thing you want to be u? Okay, looks like everyone has replied A here. That is correct. And the reason for that is because, well, if you let u be equal to 4x, then du is equal to 4 dx. And so this entire thing is equal to the integral of 1/4. Oh, I used an exponential again. I probably should have used a different thing like a sine or a cosine, but the basic idea is still the same. That's 1/4 e to the du, which is equal to 1/4 e to the u plus some constant, which is equal to 1/4 e to the 4x plus some constant. Okay, let's try one more before we move on. So this one's slightly more complicated, right? So we have 12x times the... Oh, sorry, let me reset that quickly. So please answer your thing again, because I hadn't reset it yet. Okay, so we're getting a couple different responses. We're getting mostly B's, but we also got one D. So, this is actually a good thing. So, a lot of you are suggesting 1 plus 6 squared. Some of you are suggesting 6 squared. And the question is, what happens when you do both? We're also getting a C. So, let's try a couple of these different things. So now, the trick is you want the derivative to be, you want du to be something that, roughly speaking, appears. And there are a couple of different ways you can have this work. And the reason I put this problem on here is because there are a couple of different answers that will all work. But they'll work in slightly different ways. So the most obvious one here is u is equal to 1 plus 6x squared. So this is the one that, if you chose it, would make your problem the simplest. But even if you choose a slightly different one, that hope isn't necessarily lost. So let's suppose that we tried, looks like the second most popular answer here is D. So let's suppose we tried u is equal to 6x squared. And let's see what happens. Well, then du is going to be equal to 12x dx. And so this thing is going to be equal to the integral of the square root of 1 plus u du. Okay? So the question you should be asking yourself after doing u substitution is this simpler? And the answer is yes, this is simpler. Like, it's maybe not quite as simple as you want yet, but it is simpler. So then what you might do is you might do another u substitution, or you'd have to choose a different variable name because you've already used u. So let's suppose I have a different variable name called v. Let's say I did another substitution, a v substitution this time, of 1 plus u, then dv is equal to du, and so then this is equal to the integral of the square root of v, so v to the 1/2 dv, which you also know how to solve. And so that's the trick here, is that each time you do a substitution, you want to make it simpler. And if you're really clever, you can make it super simple in one fell swoop. So if you had used u is equal to 1 plus 6x squared, then you'd have jumped 2 steps at once. But if you do something wrong, but still makes it, or sorry, not even wrong. If you make a choice that is suboptimal, but it still gets you to a more simpler expression, that's still progress. Because then you just have to do another substitution to get it even closer. Okay, so hopefully that gives you a little bit more of a sense of how to deal with these sorts of u substitutions. You want to try something where the du, roughly speaking, appears up to a constant factor in your original integral. The u factor doesn't have to be part of your original integral immediately, but it should be something that when you substitute it in, it basically cancels out all the remaining x's. Because you need to get rid of all the x's somehow. Because you need your integral to just be in u. Okay, so that's all I'm going to say about u substitution. Practice it. If that doesn't make sense to you, you should practice some more. And you should get quick at it. You should be able to immediately identify, like we just did, what a substitution might be that ought to work. Okay, so now let's get to what many people find slightly harder. Let's talk about integration by parts. So now the integration by parts algorithm, we also had a guessing step, right? So let me highlight that. So this first step was, again, guess which part is u and guess which part is dv. So now we had a question earlier, I think it was Samantha, but who mentioned it. Don't you want both parts to be part of the original? That's not true for u substitution, but it is true for integration by parts. Both the u and dv have to be part of the original integral formula. And you can only do integration by parts if you actually separate it out into parts, which is where its name comes from. So that once you've guessed it, then you can apply the formula and just directly solve it. And the idea is that the integral of v du should be simpler than the integral of u dv. So what does that sort of imply? That means that you want the dv to be something that's easy to integrate and the u to be something that's easy to take a derivative of. Oh, there's a really good question. How do we know when to use substitution and when to choose integration by parts? So the answer to that is a little bit complicated. The answer is sometimes both will work. And you can use either. And there's no easy rule to tell you what will work other than just trying it. U-substitution is easier to do in many ways. Yeah, exactly. So Sarah suggests when we can't do substitution, we do parts. So U-substitution is often easier to do. So if you can do U-substitution, it's easier to do it since you only have, well, one thing to do. So I would suggest you try U-substitution first, and if that fails, then you try integration by parts. And as you get more practice, you'll quickly recognize when U-substitution will fail, and then you may need to try integration by parts. For some integrals, and there are some very famous ones, like the ones that give you the normal distribution, where both U-substitution and integration by parts fail. In fact, there is no closed form way of solving it. I won't be so mean as to give you one of those problems, but you should be aware that in practice, many integrals, there's just no way for us to do. And I'll be coming around to that point in a little bit again. But anyway, let's move on. So how do we deal with this integration by parts stuff if you need to make a guess again? Well, yes, there are questions when you can do both. And I don't think I have one on my lecture today, but there are a couple examples where you can do both. And if you can do both, well, I'll give you an example. I'll put an example of that in the Piazza. If someone reminds me. If someone asks that in Piazza, I'll give an example where you can do both, and they'll both work. Sometimes they'll both work and give you answers that look slightly different, but they will actually be the same. But yeah, someone asked that in Piazza. Okay, so now let's go talk about some examples of integration by parts and how we pick the u and the dv. So let's see a couple examples first. So let's say we had the integral of ln x dx. Well, we have two different parts, right? So let's say that we let u be equal to ln of x, and we let du be equal to 1 over x dx. And let's say, well, that leaves this to be dv, right? So dv is equal to dx, and that means v is going to be the integral of dx, which is going to be x. We don't care about keeping the constant here because we'll have another constant in there, and all the constants cancel out, or lump together. So by using integration by parts, you get that this is going to be uv, which is just going to be x ln of x, minus the integral of v du, which is going to be x times du, which is 1 over x dx. So that's just dx again. So this is equal to x ln of x minus x plus c. So note that what's important here is that ln of x is easy to take an integral. Ln of x is easy to take a derivative of, and dx is easy to take an integral of. And we'll see that again here on the next one. So let's say we have x cosine x dx. Well, in this case, a good choice would be u is equal to x, because that's easy to take a derivative of. Du is equal to dx. And then this turns out, sorry, that's an s. That was supposed to be an x. Cosine x. And so if dv is equal to cosine of x dx, then v is going to be the integral of that, integral of cosine x dx, which is just going to be sine x. And then you plug in the formula, and then you're done again. So this is going to be x sine x minus integral sine x dx. It's going to be equal to x sine x plus cosine x plus c. Now some, wouldn't du be 1? Oh yeah, sorry, it's 1 dx. So, because 1. Because what I'm doing is I'm separating the du over dx, and then I'm multiplying both sides by dx. So, strictly speaking, if you were in a math class, I would now be waving my hands and telling you you can't ever do this because it is not formally defined what the du and dx are, because we don't have the machinery of hyperreal numbers. But it turns out in practice, for most engineering and science purposes, you can pretend that these du and dx's are things you can multiply around. If you're interested, you should take a higher math class and learn about hyperreal numbers. But we're not going to worry about that today. The other way you could do it is you could, I could write out a super long delta epsilon proof for all this, but since you're in the math for biology class, we're not going to worry about that. Okay, so the trick was that we want to separate into one part that's easy to integrate and one part that's easy to differentiate. And I'm about to give you a heuristic, which gives you a hint as to when that is the case. So this heuristic has an acronym. Someone came up with this a couple decades ago, basically to teach calculus students. And it's basically a list. So functions near the top of the list have easy antiderivatives, and so are good guesses for dv. Functions near the bottom of the list have easy derivatives, and so are good guesses for u. So d might be, so dv itself, the d at the top just is the reminder that the top of the list is things that are good guesses for dv. Then we have exponential functions, trigonometric functions, algebraic functions, so things like polynomials. I for inverse trigonometric functions, like arcsine, arccosine, things like that. And L for logarithmic functions. So things at the bottom have easy derivatives. Things at the top have easy antiderivatives. And so these things are good guesses overall for these kinds of things. Note that there are some exceptions to these heuristics. So sometimes the I and the L are swapped. So sometimes you need to do an integration by parts where you swap a couple of these things. And this is just a heuristic. And sometimes you need to split a single algebraic function into two pieces, if like the two pieces are both about the same level of easiness for derivatives versus antiderivatives. But the basic idea is, as a general rule of thumb, you want your dv to be easy to integrate, and you want your u to be easy to differentiate. Will we be working with inverse trig? Sometimes, yes. And I will talk a little bit more about that in a moment. Relatively little, just because, I am about to give you a list of a bunch of tables, which I will, some fraction of which I will give you on the exam. So I don't expect you to memorize all the inverse trig identities. I will give you those, the inverse trig identities, but you still need to be able to work with them. Okay, so let's give an example of how this might work out. And how am I doing on time? Okay, I'm still doing fine on time, hopefully. So let's give an example. So let's say we had the integral of x squared e to the minus 2x dx. So now the question is, what part of this is easy to integrate and what part is easy to differentiate? So you'll note that we have an algebraic piece here, right? So we have an algebraic piece here, which is this x squared, and we have an exponential piece here, which is this e to the minus 2x. So we have both of these pieces. So that is a good first guess for u and dv. So let's guess u is equal to x squared, du is equal to 2x dx, and then dv is going to be equal to e to the minus 2x dx, and then v is going to be equal to minus 1/2 e to the minus 2x. So you might notice that I just played super fast and loose, and I just did a u substitution for minus 2x when I was taking the integral of e to the minus 2x dx. That is how fast you need to be at like the very basic integrals and the very basic u substitutions, because those are just things that you need to be able to do on the fly, since they form such a since they often show up in the more complicated problems. Okay, but so now let's do that. And so what do we get? We get x squared times, so that's u times v, which is minus 1/2 e to the minus 2x, minus the integral of v du. So v is going to be, again, minus 1/2 e to the minus 2x. Du is going to be 2x dx. So if we rewrite this slightly in the nicer form, this is going to be minus x squared over 2 times e to the minus 2x, plus the integral of x e to the, so you'll notice that the minus signs cancel out, and the 1/2 and the 2x also cancel out. So this is just x e to the minus 2x dx. So now you're not done, but this integral is at least simpler than the one you started with, right? So this is a simpler integral, and let's do it again. So again, we have some part that's algebraic, and we have some part that's exponential, and you can repeat the process. So u is equal to x, du is equal to 1 dx, but I'm just going to write dx here. And we have dv is equal to e to the minus 2x dx. Of course, we already solved that one, so that's v is equal to minus 1/2 e to the minus 2x. And you end up with another integration by parts. And so this overall is going to be minus x squared over 2 e to the minus 2x plus this new integration by parts, which is going to be minus x over 2 e to the minus 2x minus the integral of minus 1/2 e to the minus 2x dx. Sorry, I went over it a little bit. But now that we've done that, well, that is finally an integral we know how to do, right? So if we rewrite all this out, this is going to be minus x squared over 2 e to the minus 2x minus x over 2 e to the minus 2x plus 1/2 times the integral e to the minus 2x dx. So this is going to be, let's copy all that down. And this is going to be minus 1/4 e to the minus 2x plus c. Okay, so that's how you use this heuristic. You basically, you break it up into two pieces, and then you're like, well, which piece is easier to integrate and which piece is easier to differentiate, and you try that as your guess. It won't always work, but at least it'll give you a starting point. And if it doesn't work, then you might need to try mixing and matching a little bit. Okay, so let's have you guys try it out. So I'm giving you a couple hints. So one thing to mention is that when you have a definite integration by parts, you just do the 1 and e, the limits at the very end, as usual with an integration. You don't have to do any substitution unless, you don't have to do a change of variables like you do with substitutions. Now, just as a hint, note that we might have an algebraic piece, and we might have a logarithmic piece. So that is your big hint. So note that you have a logarithmic piece, and you have a... okay, yeah, so I'll slow down a bit, especially now that we're giving you guys an example. So we have a logarithmic bit, and we have an algebraic bit. Thank you for reminding me that I speak quickly. Yeah, I remember some of my students in one of my last classes mentioning that they would watch me on 0.75 speed, which I'm not sure if that was a complaint or... I'm pretty sure it was a complaint, but yes, you should remind me to slow down. But yeah, so we have these two different pieces, and so that gives you a hint as to where to start. So now, the logarithmic might be a good choice for you, and the algebraic part might be a good choice for v in this case. And so, well, let me just go ahead and write that down since I've already told you that. And you guys should be working on this with me, hopefully ahead of me. But u is equal to log of x squared, and so that means du is going to be equal to 1 over x squared times 2x, because by the chain rule, which is going to be equal to 2 over x. And we have our dv is going to be equal to x dx. And so then v is equal to 1/2 x squared. So hopefully that gives you enough hints to be able to at least write down the indefinite, the antiderivative, and then you just need to plug in 1 and e. I'll give you guys a minute or two to work on this before charging forward, and also a moment for, I guess, both you and me to catch our breaths. Oh, I may as well also take this opportunity to remind you all of a fun little fact about logarithms. So log of x squared is equal to 2 log of x. So these are things that you should keep in mind. So we have one guess, which is e, so none of the above. Well, let's see what other people get, and if people agree on that. So b with a question mark. Let's see, b with a question mark, and some b's. Okay, so let's work through this, because So the first thing is this is the integral from 1 to e of x ln of x squared dx, which is equal to, well, by integration by parts, this is 1/2 x squared ln x squared from 1 to e, minus the integral from 1 to e of x dx. So that's equal to 1/2 x squared ln of x squared minus 1/2 x squared, all of this from 1 to e. And when you plug all this in, what you'll find if you don't accidentally make a math mistake is this is 1/2 e squared ln of e squared minus 1/2 e squared minus 1/2. Now, of course, note that this here is just equal to 2 by properties of the natural log. And so this is equal to 1/2 e squared plus 1/2. So that is indeed B. Oh, the poll didn't update. Come on, poll, you can do it. But yeah, so like my guess is like some of you just made arithmetic errors, but you do need to be able to like manipulate these things algebraically. Yeah, it looks like most people got B's. So nice job. Okay, so now we've been spending a lot of time in math land, and it's important for a math biology class to take some time and step out of math land back into the world of biology. So what's one example where you might do this? So one example would be drug dosages. So suppose you have a patient that takes 25 milligrams of a drug orally, and we know that it's metabolized from the body at a rate of t e to the minus kt, where k is equal to 0.2 milligrams per hour, and t is time in hours since taking the drug. And so I've drawn out that metabolic curve over here on the right. Now, you might ask how you know this is the metabolism rate. Well, that is something you can figure out using, well, biology. And this is actually a relatively realistic, simple model of drug metabolism. For like the time it takes your body to excrete a drug, sometimes through urine, sometimes through metabolism and metabolizing and then breaking it down. So now the question is, how much of the drug has been metabolized after 10 hours? Now, as we've talked about, one of the big advantages of integration is that you can find areas under curves. And so what we want to do is we want to find the area under the curve here. Okay, so let's do that. What do we do? So we need to take the integral from 0 to 10, because we're time from 0 hours to 10 hours, after the drug has been ingested, t e to the minus kt dt. So now we have several different parts, one of which is we have an algebraic part and we have an exponential part. And so we can let u be equal to t, du is going to be equal to dt, v is going to be, dv is going to be equal to e to the minus kt dt. And so v is going to be equal to minus 1 over k e to the minus kt. I'm leaving it as a k just because it's a little bit easier to write than 0.2 every time, but you can substitute in 0.2 everywhere you see that. So this is going to be equal to minus t over k e to the minus kt from 0 to 10 minus the integral from 0 to 10 of minus 1 over k e to the minus kt dt. Sorry, I'm running a little bit out of space. And when you plug this in, this is going to be, you can plug in the 10s and 0s for the t's, and you can plug in, well, k is equal to 0.2. This is minus 10 over 0.2 e to the minus 2 minus this quantity, which is going to be 1 over k squared e to the minus kt from 0 to 10. And so when you plug all this out, you'll need a calculator because you presumably you don't have e to the minus 2 memorized, though if you do, all the more power to you. So this is minus 50 e to the minus 2 minus 25 e to the minus 2 minus 25. And so this is equal to 25 minus 75 e to the minus 2, which you'll find is approximately 14.85 milligrams. And so this is one of the sort of practical applications for using this sort of integration, is you can understand how much drug has been metabolized after some amount of time in a human body. Okay, so now this is a really good time to take a brief interlude and talk about why you guys need to know all this stuff. So I know we've talked about this before, and then we had the example of people reinventing the trapezoid rule, but, oh, sorry, that's not the right button. But there's a lot of difference between theory and practice, and this is a math class, so it does cover a lot more theory than you'll probably be using in your day-to-day. So now, why should you practice all these integration techniques when a calculator can do the same thing? In fact, there are a number of practical tools that are helpful to you. One of them is these integral tables. Actually, let me, I need to get this integral table up. And a lot of the things that I'm teaching you how to do, come on, integral table. Ah, there it is. Let me switch over into my Chrome capture. So, you know how there are a bunch of these complicated integrals? Actually, let me move myself over here. Okay, you know there are a bunch of these complicated integrals? It turns out that mathematicians have had a lot of time on their hands in the last several centuries, and they have spent a lot of time just going through and trying to compute integrals of everything they can. And there are these tables which are quite useful because if you can change your variables using a u-substitution to look like one of these tables, you can just look up the answer. Some of the easier ones I have listed here, I gave you in your your table that I ask you to memorize. So like here's this integral of sine of ax, which is one of the things you have to memorize. But then there are all these more complicated ones, like sine squared also has a integral here because someone's spent the time to compute it, and so on. Let me zoom back out. And so there are these giant tables, and if you were ever going to do an integration in practice, you would obviously have all these tables available to you. These tables don't cover everything, obviously, because you might have to do a change of variables to look like them, but the basic idea behind the sort of task of integration is doing all these various transformations to get it into a form that we already know the answer to. And there are many common ones where we already do know the answer. So why am I making you do this? Because you still need to know these techniques to be able to change the forms around if you're ever actually going to do an integration. But now you might be saying, well, like when am I ever actually going to do this? And the answer is probably never, because there are also other calculators you can use. For example, there are online calculators that you can use that will often do a lot of this work for you. So for example, if you go into Wolfram Alpha and ask for the integral of x ln of x squared, it will just tell you the answer. And of course, if you actually want an integral under a curve, you can use something like Desmos. Yes, Desmos is on there as well. So you can use something like Desmos. It's a great online calculator, and you can explore what happens when you're integrating over different regions of the curve. And these sorts of numerical integration algorithms are really powerful, and often they're used in practice when we can't actually complete the explicit integrals. And you should be aware of all these different tools, because these are the sorts of tools that when you're actually using integration, you will have to use this. Or you won't have to use this, but I would suggest that you make extensive use of these tools when you're actually doing these problems in the real world. Not in this class, but in the real world when you're doing it, you will be using a calculator. And it would be wrong for me to tell you otherwise, because in the real world, when I do these things, I also make use of calculators, unless it's something super complicated that the calculator doesn't have an easy answer for. And so for hard problems, the calculator might not have an answer, but it might. And it's important for you to know how to use these tools. So, having said that, why should you guys care in this class? Well, there are reasons that you should practice what calculators can do. And you guys had to do this back in high school and grade school when you had to practice addition, subtraction, multiplication, and all that. And oh wait, what just happened? I just clicked on the link. That was silly. Come on, go back to PowerPoint. What just happened? Okay, sorry, technical difficulties. That's what happens when you put links in your PowerPoints and you accidentally click on them. So why should we practice what a calculator can do? One is that these are building blocks for more advanced techniques, and you will need to do these more advanced techniques in analyses. So you note that the integration part of this class is actually really only the first couple weeks, and then we're moving on to more advanced techniques that build on these building blocks. The other is so they have some intuition for when things go wrong. So like, if you take an integral of a strictly positive function and you get a negative number, then you know something went horrendously wrong. Because an integral of something that's strictly positive, so the area under the curve is going to be positive, and so therefore you should get a positive number. And so building that sort of intuition is also really important. And the last thing is you should understand how calculators work so that you can modify the algorithm when faced with a slightly different problem. And this brings us to, where's my next slide? This brings us to numerical integration. So I'm going to teach you how some of these online calculators work to compute the area under a curve. And we already sort of discussed this, because we discussed how you can approximate the area under a curve by dividing into shapes you know how to compute for, like rectangles or trapezoids. And earlier we used this to prove, well, sort of prove, to show you what the proof looked like of integration. Like if you have infinitely many rectangles, then you get the actual area under the curve. But when you only have finitely many rectangles, you still get an approximation of what the actual area is, and you can do even better by dividing into other shapes, like trapezoids. So let's get started, talk a little bit about the Riemann summation rule. So, yeah, where was I? we're going to break it up into a bunch of rectangles, right? And then, as we discussed last time, the area is equal to the sum over I equal 1 to n of delta x times f of xi, where each of our xi's are the different points along the that we've divided that separate the rectangles. So that's equal to delta x times the sum of all these values from 1 to n of f of xi. And so one way you can see this is if you draw out a table of all these things. So if you were doing this by hand and you didn't have a calculator, what you might do is you might write out your I here. So that's 0, 1, 2, 3, 4, all the way to n. And you might have an xi here, which is going to be equal to a plus I delta x. And that's going to be x0, x1, x2, all the way to xn. And once you've written out all these things, then you might have f of xi. So you compute whatever function that is. And then now I'm going to write out the summation in a weird way. Because this is going to play a role in some of the other approximation techniques. I'm going to put a weight. So I'm going to put a weight on 0 because you don't have a copy of x0 here. You start from 1. And a 1 everywhere else. And then I'm going to say that our term here for the summation is going to be the weight times f of xi. And then what we can get is if you sum all these terms together, you get the sum from I equal 1 to n of f of xi. Okay, so this might seem like a super weird way of doing it, but it is helpful if I force you to do one of these Riemann summations by hand, which I might do. I haven't decided if I'm not mean yet. I might be, so you should watch out. But if I force you to do it on the quiz, it will be on the practice quiz, of course. So now, what are other things we can do? We also have the trapezoid rule, right? So what does a trapezoid look like? So in this case, we're dealing with very specific trapezoids, which have a flat base at the bottom. So how do we get the area of all these things? So if we have a trapezoid, if we have these trapezoids, because they have a flat base, you can divide them into a rectangle and a triangle, where here is height 1, and here is height 2, and this is your base, which is delta x. And so what is the area of this trapezoid, this particular trapezoid? Well, the area is going to be equal to, well, we have delta x times h1, because that's the amount of stuff in your rectangle, plus your triangle. The height of the triangle is, so the base of the triangle is delta x again, and the height is h2 minus h1. Sorry, let's send h1. And therefore, that means that the area of this trapezoid is 1/2 times delta x times h1 plus h2. So what is that area under the curve equal to? So if you take all these things, note that our h1 here is going to be some, what color am I using? Let's use orange. This h1 here is going to be some f of xi minus 1, and this here is going to be some f of xi. And you can compute an area under the curve this way. So the area under the curve using the trapezoid rule is approximately equal to the sum from I equal 1 to n of 1/2 delta x times f of xi plus f of xi minus 1 from 1 to n. And if you write this all out, this turns out that's going to be 1/2 delta x times f of x0, because even though we're starting with I equal to 1, we have a term of f of xi minus 1, and if I is equal to 1, then that's f of x0. But then we have two terms of f of x1, because we have the term from I equal to 1 of the f of xi, and then we have the term from I equal to 2 of f of xi minus 1. And you have two terms of all these other ones. Why is it minus 1, not plus 1? Oh, so if you start from I equal to 0 to n minus 1, then it would be plus 1. So it's just a change of variables. So it would be equivalent to say the sum from I equals 0 to n minus 1 of 1/2 delta x f of xi plus f of xi plus 1. So it's just a matter of which index you're starting with. And I started with index 1 because that's what we did with the Riemann sums. Okay, so all the way to plus 2 times f of x n minus 1. And then, of course, you only have one copy of f of xn. And this makes sense, right? Because the question is, for each of our values, how many trapezoids is it a part of? So for the two n trapezoids, it's only part of one of the n points, it's only part of one trapezoid, but for every one of the points in the middle, it's part of two of them. And so you get twice that. So this gives you the trapezoid rule, which, let's see, if we keep all that, and what I'm going to do is I'm going to draw out a similar table. So let's going to have our I, 0, 1, 2, all the way through n. Let's say n minus 1 and then n. Of course, we have our xi's, so x1, x2, x3. Oh, no, starting from x0, sorry. It's important that you start the indexes correct. That's a really easy way to make mistakes. x0, x1, x2, xn minus 1, and xn. Then you have your f of xi, which is just whatever the value is. But the important thing here is the weight is actually going to be different. So the weight's going to be 1 for the first term, 2 for the second term, and 2 for all terms except for the last one. And then we have another term here, which is going to be the weight times f of xi. And here, this summation is going to be equal to all the stuff that's in green. Okay, so now let's see this in practice. So let's give an example. So I have computed, what I'm doing here is I want the numerical integral from 0 to 1 of 1 minus x squared dx. So this is an upside down parabola that intersects at the point, at the y-intercept of y equal to 1. And I want to do it with n equal to 10. So with 10 data points, or sorry, 11 data points, because you want to go from x0 to x10. So a is equal to 0, b is equal to 1, and these. Why do you start with I equal to 0 in the table? So the reason for that is because for some of these approximations, as you see here, we have a trapezoid weight. In the trapezoid weight, the I equals 0 term actually has weight. And so for the Riemann sums, the I equals 0 term doesn't have a weight. But for the trapezoid terms, it does. And so that's why I start with I equal to 0. You have 10 trapezoids, but you still need to take into account 11 different terms to figure out the area of all the trapezoids. And so if you look at this table, what you'll notice is that I've done both the Riemann's weight and the trapezoid terms. And what this is just drawing them all out. And you can compute the total sums from this table. So the sum here is going to be 6.17, and the sum here is going to be 13.34. And you're going to be left with a Riemann area of 0.1, because that's the value of delta x, times 6.17, so that's equal to 0.617. Note that the actual area under the curve is 0.667, or 0.6 repeating, which you can get from the integral if you do it analytically. The trapezoid area is 0.1 times 1/2 times 13.34, because that was the formula that we had, and so that's equal to 6.67. which is a better integral, though it's a slight overestimate. And sometimes so note that the way I've written out this table, it sort of implies that sometimes I might want to put different weights into the table and then sum up the terms differently. And so I'm going to introduce you to another approximation method that sometimes people like using called Simpson's method, which is the rule of thirds, because you have this other set of weights, which is in a sort of weird way. It basically tries to oh wait, sorry, did I do something wrong there? 0.667, 0.67. Oh, yes, wait a moment. It is. I definitely did that wrong. So thank you for catching that. So that's 0.667. So that's a pretty good approximation. Oh, no, wait, sorry. That actually is 0.67, which, did I do that wrong? I definitely did that wrong. Sorry. Let me actually write down. I'm trying to go too quickly. So that is actually from looking at my notes, which look like they're actually wrong, but it is 0.667. Note that this is actually 0.666 repeating. So it's not exactly perfectly accurate, but thanks for catching that. Okay, where was I? So the trapezoid area, so that was actually a pretty good approximation. Sometimes you might want to use other approximations, such as this weird one here, Simpson's rule of thirds, which you might hear about sometimes when people are actually numerically integrating. where instead of having 1, 2, 1, and then a bunch of 2's and then 1 for your weights, you have 1, 4, 2, 4, 2, 4, 2, 4, 2, etc., and then the 1 at the very end for the weights. And this gives you a different sum. So this gives you a Simpson sum of 20.04, and it's the rule of thirds, so you're actually dividing by 3 instead. So these are just different approximations with slightly different shapes. These shapes are parabolas instead of rectangles or trapezoids. And you can try approximating all sorts of different shapes. So this is going to be times 20.04, which is going to be equal to 0.668. So this time it didn't seem like that approximation was that good. Why do you use 4? Because it's a parabola. So the derivation of that is not actually in your book. The derivation of that is a little bit complicated, so I'm not going to spend too much time going into it. But yes, it has to do with the fact that it's a parabola, and those are the weights that you need in order to get the right shaped parabolas for this sort of approximation. Basically, the point is that when you have all these different samples from your, when you have all these different samples, you don't actually know in advance what shape your real function is, and so you have to do some approximation. And that brings us to the next point, actually, so I'll talk a little bit more about this afterwards. So, what do you guys think is the most accurate approximation? So is it the Riemann approximation of rectangles? Let me reset this before you guys start replying. So I've given you 3 different approximations. Which of them is the most accurate? Riemann, trapezoid, Simpson, or is it one of B or C? So trapezoid or Simpson, or is it none of the above? And let's see what people give. Oh, this line down here was not supposed to appear until after I finished writing. But, so we, oh, it looks like I'm also about out of time. So let me just finish up quickly. So it turns out that which approximation is the most accurate depends on the exact function you're integrating. So for example, if you had a function that looked like this, then, which is a super weird function, but if you had a function that looked like that, then even the Riemann sum might be the correct one, because you might have, you might get these rectangles. So usually the Riemann integral will not actually be the most accurate, but occasionally, with some functions it will. And it really depends on what shape the function you're trying to approximate is. And so the real answer here is none, because it depends on what you're approximating. It depends on what you're doing. And our normal intuition is that most of our functions are smooth. And for smooth functions, trapezoids are better than Riemann sums. And sometimes if your smooth functions are parabolic, then Simpson will be better than trapezoid. But it really depends, and you should make a decision based on what you think your actual curve looks like. So the accuracy of the approximation depends on the function. And that brings me to my last slide, and then I will let you guys leave. So, what is the area under an experimentally sampled curve? Well, that was the whole thing about the trapezoid rule being reinvented that I showed you in the first class. And the thing is, when you don't have an exact formula for a curve, you might think, well, we can't integrate it, right? Because for an integral, you need an actual curve. But it turns out we can still treat our discrete measurements as samples of f of xi, and then our numerical integration techniques that we just discussed actually do apply. And so even if you don't have something that looks exactly like your function from calculus, you can still use these ideas from integration to use these numerical approximations. And so that's one of the reasons why it's important that you understand the ideas behind integration, because it lets you know when you should apply related approximations. And with that, I will finish for the day. Sorry.